Yeah, so thank you for coming. Good afternoon. So my name is Yanfa Yan. I'm from the University of Toledo, as in Ohio, USA. There's another University of Toledo in Spain. I just want to point out. So today I'm going to talk a little bit about the theory of metal Halide Perovskite. So I know this university is very, very different. So lots of different areas. So if you work in material science, every once in a while there will be buzzword. So some time ago, you heard about superconductors. Everyone is talking about superconductors, and then sometimes people talk about the nanomaterials. Everyone talks about nanomaterials, but in recent years, so there's a buzzword called the perovskite. So it seems everyone talks about a perovskite. So today I'm going to share with you about what is a perovskite, why this material is so fascinating, and why there's so many people working in energy material area that care about a perovskite. Indeed, perovskite is a very, very intriguing material. And today I'm going to show you some of the properties from the theoretical point of view. So get a long list, but I'm not going to go through this. But I will begin with this photo, which was taken just a week ago in Los Angeles, LA. So you may want to go to LA to see Hollywood. I don't know if Hollywood is impacted by this because I'm not there, but probably yes. At least the climate, the weather is lots of dust area. So if you look at the image, right, it's a fire. So very, very severe, devastating fire in the LA area. So there's the bigger fire, right? There's a bigger fire you can see is Los Angeles. It's very, very close to the city, the center of the city. If you look through the city, so this is this disaster in the daytime. Okay, so it is very devastating in LA, and this is not the only time there's a wildfires. Actually, in California, in San Francisco, there are multiple fires. So those fires, they are caused by the climate change. At least I believe so. Even though there are many people that don't believe so. But if we look at this video, I want to show you that I downloaded from NASA's website from here, right? You can see in the past few centuries how the temperature has come up. So you can see in recent years, so now 1960s, you can see immediately we see how the temperature is getting hotter and hotter on the Earth. So you can see it is quite dramatic. So now in the last 2 years ago, you see now it's everywhere it's getting hotter. You can see where more people, the temperature is higher, then you see the temperature got hotter. So definitely the environment in our Earth is impacted by human beings because of course we burn lots of fossil fuels and then we raise up the temperatures. So this figure shows how much the temperature has increased in the past about half century, right? So in some regions, particularly in this region, the North Pole, the temperature change is so dramatic, 4 Celsius, which is a lot. As a consequence, you see the North Pole, the ice, right, has shrunk dramatically over the few 20, 30 years. And there's a severe consequence. So like the polar bears starving, and I hope if we do not address this issue, the next will be us, not the polar bear. We'll suffer from the same issues. Therefore, we need to do something on the environment. So I think energy, the burning the fossil fuel is number one impact on the temperature. So talking about the renewable energy and the sustainable energy. So solar energy, right? Solar energy gives us the most unlimited source for energy. So I get this one from the National Renewable Energy Laboratory, right? So get the sun solar energy. So therefore, that's the reason why in the past few decades, the research on solar energy has considerable effort and put in the solar research. So showing here, this is very famous, the so-called best research laboratories efficiencies. They summarize all the technologies people have been investing in the last few decades. And you can see all the solar technologies, the efficiencies that will increase as the time goes, because we spend more time to understanding, right? So more or less to follow this kind of a trend. However, there's one quite unusual trend, which is indicated by this yellow dot. So it increases so dramatic, and then in about a decade. So the efficiencies has climbed towards to where, like the silicon, people have spent decades to get this efficiency. So this is the so-called perovskite. And that's the reason why perovskite becomes so famous. So many people are working on perovskite. So if we just look at the numbers of publications and over the years, right? So it increases exponentially, right? And then as for us as a scientist, we get attention, we get attraction, mostly because of the publications. So if people publish lots of papers in Science, Nature, and all those high impact journals, then we will be attracted. So you see on this paper, I got this from Web of Science. So for perovskite, all topics increase so dramatically. And if you look at the others, so if you look at this Nature family, right? So people publishing in Nature family journals, and then you see it's also increased dramatically. This is why people are so interested, so fascinated by this material, because they can help us to make a good publication, which is good for scientists. And for perovskite, not only being used for solar cells, and also people using for other areas. Like say, there's for solar cells and for photodetector, LEDs, right? Light-emitting diode, laser, and many others. So you can see all the publications. They are so wonderful. So in the last decade, it's just a decade or so. So the change, both the publication and also the device performance increased dramatically. So what is perovskite, right? So perovskite is actually it is a type of a structure, crystalline structure. So it was given after a Russian scientist who discovered a mineral. A top of a mineral is oxide. It's the beryllium titanate. It's literally is the name of perovskite is given by this kind of a mineral. It's a kind of a structure. So this structure has a very unique has a very unique feature, which is that so we have a ABO, those kind of structure. So it has this octahedra. They have color sharing, forming this kind of network. So this structure has a very high symmetry. It has OH symmetry, which is the highest symmetry. So which is very important. So originally this structure was given for oxide, but later on people just give me to say for this particular structure is you have a calcium, the large atom in the space, and the octahedra is that you have titanium in the center and you have oxygen at the corner. So this is the oxide perovskite. But then later on, there are other oxide, which is called a halide perovskite. So for the halide perovskite, you have a similar formula ABX. So in this case, it's no longer oxygen, but it's an anion, it's oxygen, not it's a halide, like say either chlorine or bromine or iodine. And then in the center will be another cation, usually, and for the halide perovskite is a lead or tin. And then you have another larger cation, either cesium or another organic cation, because in order to survive when we need a structure, this cation must be large enough because the lead atoms, the iodine are too big, so you need to have this one. And there's a formula we call the tolerance factor to describe the stability of this structure. And so that means not all elements come together will form the structure. So the size of the atom, there's some requirement for the size in order for them to come together to form this. So this material, this halide oxide, and has been known for centuries. It is never been used. So when Professor Tomi Miyasaka at Torin University, and he was studying the so-called dye-synthesized solar cells. So to dye-synthesized solar cells, you usually use a dye, organic dye, and put it on a titanium oxide framework. So this dye will absorb sunlight and produce electrons, and the electrons will be transferred to the TiO2, so you make a solar cells. And then, so those dye, the best dye at that time is the uranium dye, and again, the efficiencies are not very high. So people are trying to find a different dye to improve the efficiency. So Professor Miyasaka, he, for the first time, he tried putting this kind of halide perovskite, which is this one, the bromide, instead of a dye. He put this one on the TiO2 scaffold. And he was able to make a dye-synthesized solar cell, which is about 3 to 4%. So that's the beginning of the halide perovskite solar cell. And then after that, after 2 years later, when people made some modification, not exactly dye-synthesized solar cell, instead of using this liquid electrolyte, people use organic electrolyte or organic material, and so the device then becomes better, and the efficiency increased very, very dramatically. So there are different, in terms of structure, there are different perovskite. Like say, there's the original oxide perovskite, and then we have a halide perovskite. You can also have a chalcogenide perovskite. So there are many perovskite. However, only the halide perovskite are able to give us very high performance solar cells, photodetectors, or LEDs, right? So this question comes, why? Why the halide perovskite? So why not the halide perovskite? Is not special? And if it's special, what makes it so special? Now, why this perovskite, not the other perovskite, work in the market? So in order to tell this, I want to introduce a little bit about the solar cells. So this actually, solar cells is something quite simple. So solar cell, the effect, the photovoltaic effect has been discovered way back in 1876. So the first solar cell was made with solid selenium, which is a semiconductor also. So what do? You can just use an absorber, like say selenium. You put a front contact, like say transparent electrode, and then you put another contact in the back, called a back contact. Then you shine another light, and then absorb the light, and then you generate the electrons and the holes. The electrons, they will be separated by the field in this device, and the electron will go the other way, also go another way, then you will build up, just like you have a water dam, and then you build the potential here. Of course, this will be electrostatic potential, and then you will make a solar cell. So it's quite simple. If you look inside into the device, and then the absorber is a semiconductor. So a semiconductor, and that can be described, for semiconductor, described by the occupation of the electrons inside the semiconductor. So we often describe them, you have different states for the electrons to occupy them. So when all the states were occupied, the most occupied states, we'll call them valence band. And then there will be unoccupied band, we'll call it conduction band. So for semiconductor, is that the valence band and conduction band, there's a gap, right? We'll call it the bandgap. So the bandgap is moderate, then we call it semiconductor. If the bandgap is 0 or negative, then there will be conductor. If the bandgap is very large, then we call them insulator, right? So for semiconductor, which is usually the bandgap, is equivalent to the sunlight, the most abundant photons, like say the blue photons or the green photons, in the range of 1.5-ish electron volt. So when we have a semiconductor, when sunlight shine on it, the sunlight, which are photons, they will be absorbed by the electrons in the valence band. When the electrons become energized, they will jump on to the conduction band. So this is how we the so-called the formation of electron hole pairs. So I have electron holes here, electron there, and then there's another thing described the energy position of the electron holes. We call the Fermi energy positions. So without sunlight, there's just one electron that will be there, right? The static scenario. And then there's the Fermi level. When we create the electron holes, then will be a Fermi level for the electrons and a Fermi level for the holes. And then you can simply consider those energy levels are the energy for the electron holes, the usable electron holes, right? So then when they separate and they have electrons this side, hole this side, and you build up this energy with the voltage, right? Then you form the solar cell. So what determines the efficiency of the solar cell is those are two energy levels. So so-called quasi-Fermi energy splitting. So the larger the splitting, you will have a larger voltage, then you need the higher the device performance. The smaller, so why is it smaller? The smaller means if some electron holes, they recombine and then they generate some heat, they will get lost. So if that event happens, then the energy levels of the electrons will drop, and therefore the holes and it will go up, and then the difference will become smaller. So the splitting will become smaller. Therefore, for those devices, the open circuit voltage, the voltage will be lower, and then so your solar cell performance will be lower. So in this case, that means the causes for this splitting is very important. And what caused this change? Well, usually caused by defects. So in semiconductors, defects are very, very important. Okay, so the bad defects will cause this reduced splitting. The good ones will help the device to separate charges, right? So for a good device, we wanted to eliminate the better ones, increase the good ones, right? So now let's talk about, yes, please.
The number of photons. Thanks. How does the absolute number of photons affect the splitting and the efficiency of the device? Because you see in solar panel farms that they target mirrors on a single device.
Okay, so the number of the photons, how the impact the splitting of the quasi-Fermi splitting. So let's consider your material is perfect. So how much this will increase? It will depend on how the occupation, the density of those electrons. So which will determine on the ratio between the number of photons and the number of states of the semiconductor, right? So if the density of states rises up very quickly, and then the split will be getting larger. So let's say if you because the splitting come by this one, the splitting comes from here, right? So without the photons, and then you get here no splitting as a quasi-Fermi. There's a Fermi level. When you absorb photons and then start to split, so you have more photons, and they will split more. But then there will be a cap where it cannot go above the bandgap. So the more photons you have, the more splitting you will have. Okay, so the less photon you have, then the splitting will be less. So that's why if you concentrate the sunlight, right, you concentrate it, and then you will have more photons, and then you usually get a more splitting, get a more VOC, higher voltage. Or this is how you impact this one. But usually, in most cases, like say, one sun, and one sun. So the splitting, usually, if we do not consider the semi-equilibrium condition, usually will reach to close to the bandgap. Usually, because of bandgap, but it can be only smaller when the generated electron hole pairs are less than the photon density, which are caused by the defects. Okay. Okay, so for the Halide Perovskite, if we compare this one with other traditional solar absorber materials, they have a number of very, very interesting or important optoelectronic properties. like say, the absorption coefficient is very high, which is very important because if you have a higher absorbing coefficient, that means you need a less material to completely absorb the sunlight. And if I need a thinner material, then the generally electron hole pairs, they need to travel shorter distance to be collected. So that's good. And then the current lifetime is very important because the electron holes generally in there, if they don't have not long enough time to be separated, if they recombine, then that's not good. And then the bandgap is tunable, right? So because for different purpose. And then the defects density below, and if there are defects, you have defects, but tolerate. They are not bad, and then they will be good. So the perovskite, they present all those very, very intriguing properties that we have never seen before in other semiconductors. So the question is why? Why net here the perovskite, they can have these properties? So over the last decade, we have done quite a bit of theoretical investigation, starting from the first theoretical paper in this field. So we try to understand the electronic properties and the optical properties, and also the defect properties. So we come up with some good theoretical understanding about this material and why it's so good, and also that provides us some guidance on how to engineer the material to make it better. So before we get into the details, I wanted to emphasize this. So as I often tell my students, when you do your work, you need to always don't forget about the periodic table. So this is the foundation of our research, particularly for material science. So the periodic table is given in such a way. There's a fundamental reason why the periodic table looks like that. It tells us almost everything we need for our research. So if we don't look at this periodic table, it will be big loss. So I will often tell my student, so if you do particular research, if you want to understand more, go back to the periodic table to look at it. So yeah, so the reason is that there's not of a trend, right? It be a trend. So many of the properties, of course, if you want to get a very detailed information, you need to do more, understanding. But for many of the properties, you can get a qualitative understanding just by looking at the periodic table. Like say, for this periodic table, from the left side to the right side, how the atomic radius will change, which were very important. Let's say we form a structure, I said, to the tolerance factor, it will come into play. The electron affinity changes, increases, and then also ionization energy increase, and all of those together. When they form a semiconductor or from any material, they have they play a very important role. They determine the properties of the material. So understanding this trend is very, very important. So now let's come to some real materials. I'll put it here. So in the semiconductor that we use for solar cells, we know silicon, right? It is has been the top candidate, and which is dominated the PV market. It has been dominating the PV market. Silicon is the #1 solar cell material. And then we have the other materials as well. And then the table I show you the aerial chart, right? There are other materials besides silicon. You have 3,5 semiconductor. This is a group of 4, and a 3,5 gallium arsenide, 3,5. You have a chalcogenide and 2,6, like the cadmium telluride, and you have others like the copper, indium, diselenide. Have all those. So, and now we have a net perovskite. So if you look at it here in the periodic table, they are distributed in this region and with different locations. So the location gave them very, very different properties. Like I say, net, right, is in the bottom here, has a very large atomic number. So for this one, for this net, has something very special, other elements they don't have. Okay, so that's #1. Something is that is the electronic configuration of the outer shear of the net, which I would give it here. Outer shear is that the net is a 6s2, 6p2, right? And then this one, because in the location here, we can see the s electrons. the electron affinity changes, right? Increase this way. So there's a thing for the net. When it's form a compound, when you form the compound, this s electrons will remain. Yes, different. So usually we form a compound, we say the s electron, the valence electron becomes conduction band. But this one for the net, the s electron remains there, and you have p orbital. So this is the orbital, and then the for the perovskite, and you have this octahedron structure, and then so there's the net. You have s electrons will be a spheric, and then you have the p orbital, px, py, pz, and it is right at this angle, the rectangular angle. And for the s electron is lone pair s electron, which has a very, very important impact to the properties of the perovskite material. So showing here is just an example, and which is published by others, and I borrowed this one just to indicate. So when net and the halide to form perovskite. So if you look at this, as I mentioned, this will be that's the valence band, that's the conduction band. So what we see is that the valence band is derived from the net outer shell orbitals, and then both s orbitals and the p orbitals, right? So the p orbitals and will receive electrons from so the iodine p orbitals will receive the p electron, the electrons from the p orbital, but the s orbital, as I mentioned, the s orbital, so the s orbital, the energy is not too high, and therefore the electron will remain. So only the px, py, pz will give the electrons to the iodine P. So it forms this band. So the valence band consists of the iodine p orbital. The net also has an s orbital, and this s orbital is a non-pair s orbital. It's occupied states and it contributed to the valence band. Because of that, is occupied states. So this orbital and the occupied p orbital has anti-bonding kind of nature. Therefore, pushes the p orbital up to here. So after forming a compound with halide, it pushes the p orbital high. That has a very, very important consequence. I'll talk about this later. So if we summarize all those these bands together here in this chart, we'll see for the first generation solar cell, which is a silicon, you will see there has a strong sp hybridization. So the conduction band and the valence band both are from the silicon silicon p orbital, the sp orbitals, hybridized orbitals, and then the shape are more or less similar. So because you have p orbital and the density states that are relatively high. However, for silicon, there's one thing that is not good is because of the structure is a diamond structure. In that case, the band is not a direct, is indirect. So this is in the K space. So the conduction band minimum and the valence band maximum, they are not in the same K space. Therefore, we absorb solar photons. You cannot have a direct transition from here to there. So the only transition you have to go through some phono-assisted transition. So that makes the transition not very effective. Therefore, for silicon, the absorption coefficient is pretty weak. For the second generation, so I give a gallium arsenide. So gallium, the s orbital, will give the electrons, and that becomes the s band derived conduction band, and then the valence band will be the p orbital from the arsenide. For halide perovskite, it becomes very different. So the conduction band is the net p, and which is similar like a silicon. So it has a broader band, but in the valence band, not only it has the band, the p orbital from the halide, it also has this band from net s. And then because there's an s, it pushes everything higher. And that's one of the reasons why net halide as a salt, the band gap is not so large. If you think about any salt, usually they have a pretty large band gap because of salt and then it's ionic and then you have a large band gap. So, but net halide band gap is only 1.5 around. So this is why we can use this for solar cell. The reason why part of the reason why the band gap is small is because the valence band is up. And then the other part of the reason why is that it has a very strong spin-orbit coupling, which makes this band energy lower. That's why the reason why the gap is moderate. Otherwise, if you don't have this property like this underbonding coupling and the strong spin-orbit coupling, then the band gap will be large, will be too large for the application of solar cells. So I will talk about this spin-orbit coupling. So spin-orbit coupling is a known fact for heavy elements, which can be described by this operation, which is the how those p orbitals, outer shell p orbitals, interact with each other and form brings a coupling to that. And then the orbitals, and because of the coupling, and the bands will be lower in energy. So the strength of the coupling is very important. So from that, so if the coupling, like I say, is from I to J, which means from X orbital to Y orbital, so basically you can understand that the coupling is that I can rotate the PX to PY. And then if they are at a similar location, so it has a very strong coupling. The reason is you have this is because of this there's a structure, because the structure is just orthogonal and just the same as a PX PZ, PX PY PZ. Because of this structure, so it gets a very strong spin-orbit coupling. So if we look at the spin-orbit coupling, and it has this effect. So the effect is that if without spin-orbit coupling, right? So all the energy bands they are high somewhere there. With the spin-orbit coupling from the calculation, those bands are pushed down here. So they are coming down. And in here, not much spin-orbit coupling because it's the S band. However, those energies higher, as I just mentioned, is due to the non-pair s orbital impact to this one. So because of this, right? So we get a reasonable band gap. I call it a small band gap as compared to any other halide or salt, any salt. And then it has a higher optical absorption because of all this band, P band and P band absorption, and they have a dispersive band edges. So dispersive band edge meaning the effective mass for the carriers, electron holes, they are small because the dispersive curve, and those are due to the spin-orbit coupling and then the non-pair s orbital anti-bonding coupling. So because of those, there's a unique net electron configuration. We have and as well as the perovskite structure. We have this very beautiful properties for the perovskite. So because of that, if we calculate the optical absorption coefficient, right? So this is a gallium arsenide, and this we calculate the perovskite. So in this range, which is the solar spectrum range, within this range, we see the perovskite, the optical absorption coefficient is probably order magnitude higher than gallium arsenide, which itself is a very good semiconductor, right? So this is high optical absorption for halide perovskite. And also the band gap is tunable because for the halide, you can use iodine, you can use bromine, you can use chlorine, or you can use the combination. And for lead, and then you can substitute lead by a little bit of tin. And then even though we know the tin 2+ is not very stable, but it can substitute it and it can make it a material. So by combining different anions and here the cations, you can see you can make a material with band gaps, from as low as a 1.25 all the way to 2.4. And if you make it chloride, go up to 3 electron volts. So that's the same for a single material, halide material. By modifying those compositions, you can cover the entire spectrum of the sunlight. So that's very good because you can combine them together to make a tandem solar cells, which I'll talk a little bit later, or you can tune the band gap so that you can make it the efficiency higher. So that's for the optical properties and the electronic properties. And then I want to talk a little bit about the defects. As I mentioned, for device, defects are playing a very, very important role. If you have lots of bad defects, no matter how good properties, other properties you have, then it will not work, right? So defect. So I give here some kind of a summary about the defects. I gave gallium arsenide as an example. So they are this kind of defects. Like say you have vacancy, you have one atom is missing, right? Then you will generate a tiny bond around other atoms. Then you are interstitial. Then you put another one in, squeeze another atom in. You will generate lots of so-called round bonds. You have anti-bonds, so you have misplaced arsenic gallium arsenide, then we'll create more round bond. So for the defects, so we can categorize them as two types of defects. One is that with tandem bonds, the other one is with a round bond. So by doing so, we can understand the properties of the defects better. So when you form those two types of defects, they generate states, defect states in the band gap. So those are very related. They are related with the material you have. Like say for silicon. Silicon is a very strong covalent semiconductor. So we have silicon coming together, right? You have the atomic orbital of silicon. When together, many of them together, and then you will form the conduction band and the valence band, right? So they were split, they were pushed up, and this is occupied and unoccupied. So when you generate a vacancy, right? Like I say, we cut a bond off, I take one away, then there will be tandem bond here. So those silicon will have no one to interact. And then this silicon will introduce states that will be close to the orbital, the atomic orbital, that will give a state. So that state will be somewhere deep inside the band gap. So that's a real unit that's due to the covalency of a silicon. So if you make it more ionic, like say we use a cadmium telluride, so you have a cation and anion, so those two are well separated, right? Not like a silicon. So when you form this material again, then you will have this cation, the s orbital, say s orbital, will form the conduction band, and the p orbital will push it down, receive electrons here in the valence band. So it will do the same if you cut the bond from a donor. So you will cut this bond, right? You have a tandem bond here, right? From this cation side, you will generate state close to the atomic orbital here. So you have a donor state and you have a acceptor state. So you cut another, take it this away, you have a vacancy, there will be donor acceptor state, you will set states here. So you can see as the bond, the nature of the bond changes from the covalent to ionic. So you can see they will become shallower and shallower. So the shallower states, they are better because when they're too deep and the electrons come here and the holes come there, they will recombine, they will just generate the phonons. So following this, we want to have some material to generate a shallow states, right? So let's say we have seen the copper indium diselenide. The copper similarly, the copper, they have a similar like this. Copper, they have D states, occupied D states. Okay. So in this case, in this case, if we have a perovskite, because the valence band is pushed up by the non-pair s orbital, so it's actually above the valence band. And here, the conduction band is very close, and as I mentioned, it's due to the spin of the coupling, right? So when we form a tandem bond, like say we take this away, then we have a tandem bond around the anion, like say the iodine. So in this case, right, it will generate a defect level which will be close to the iodine orbitals. So it's somewhere here, but because of the valence band is pushed higher by the non-pair s orbital, so it becomes very, very shallow. And for the electrons, because now we take a iodine away, then the environmental net becomes changed. So that the high symmetry is no longer there, right? So if the high symmetry is no longer there, then the spin orbital coupling, the strength will be reduced. So therefore, so if that is reduced, then that for this net orbitals, the orbitals will be higher because the spin orbital is no longer there, so will be higher. What it's saying is that so for the net p orbitals, and because the reduced spin orbital coupling for the bulk material, for the bulk we still have the spin orbital coupling, so therefore the conduction bands are pushed down. But for that particular net, because the spin orbital coupling is reduced and it's getting up. So we can summarize it here from the first generation to the second generation to now to the perovskite. We can say naturally, you can see the defects, they are becoming very, very different. That's the reason why for silicon solar cells, you have to make a single crystal. You cannot tolerate any defects, right? That's why make a silicon very, very expensive, kind of expensive. But then for other the second generation, like cadmium telluride, you can make it in thin film because it's more tolerable. And then we'll come to net perovskite. So those defects, even though you have some defects, they are not going to cause lots of issues, particularly for the defects that are easy to form. And of course, there will be some anti-bonding defects, and then the anti-bonding will always give you deeper levels, but the anti-bonding defects that usually they are not many. So that's because there's a very, very unusual defect properties that makes perovskite outstanding. Right? So that makes this perovskite outstanding. So and additionally, the density of defects, they depend on the synthesis temperature. So the higher temperature and the defects will form more. The lower temperature will form less. So we know for perovskite, we can synthesize them at a relatively low temperature by solution process. So that's the reason why the defect densities are relatively low. So because of all this, and then the defect properties, they are excellent. So in this, so I would like to summarize what I have said here. So the perovskite, the reason why it's so wonderful is that you can synthesize the material by solution process at a temperature, and those thin films, perovskite thin film, they have property electron properties. They are as good as those high temperature synthesized single crystal like silicon. So that makes it so unique. So not only that for itself unique, it enabled other applications. One of which is the so-called tandem solar cells. So the tandem solar cells is because of that. So if we make a single solar cells, the efficiencies will depend on the bandgap. Because when we have when we shine when the sunlight comes onto the absorber, we have a different photon energies. So the energies close to the bandgap, they will be absorbed. They will generate this electrons and holes. But for the higher energy photons, the generate electrons, holes, they are away from the band edges, and then they will relax to the band edge through thermal relaxation. So this is a loss, energy loss, right? So, but if we have only one bandgap, there's nothing that we can do. If the bandgap is too large, then we reduce this kind of some energy loss, but then many of the photon energy lower than the bandgap will pass away, pass through. It cannot absorb it. So one way to overcome this is so-called make a tandem solar cell. So you like say we have two absorbers and put them together. A wider bandgap, a lower bandgap. The wider one will absorb the wider photons, right? And then the lower one to absorb the narrow bandgap, absorb lower energy photons. So in such a way, you can reduce the thermal energy loss. And this has been very successful in the past. In the multi-junction 3.5. So it has been demonstrated, right? So it can be very, very high. However, those devices are very, very expensive. You have to do epoxy growth, right? Maybe 2 decades ago, when I was at Enron, there was a project launched by DOE, tried to make a polycrystalline film, but they make a tandem, but it never happened. The reason is that there are a few problems. The problem that we encounter is that when you put them together, right, So when we make a particular, so when we make it one cell on the top, we also need some temperature, we need some process conditions. So when we make them, they always damage the bottom cell. So it's difficult to make them. And also when we increase the bandgap, the wide bandgap, make a thin films, and then the performance are always not good because of the defect process not good. So the perovskite just is a perfect match to make this. This is something we call a dream come true. So we can make a tandem, make a perovskite enabled tandem. So showing here over the last kind of less than decade is how much there is changed. And this one is the involvement of the efficiencies of perovskite. So here is the perovskite tandem, and here perovskite silicon tandem. And so you put the perovskite and silicon together, you make a tandem, and you see the efficiencies can increase dramatically to quite a bit, 34.6. So you can also do perovskite tandem. And so those are relatively cheaper because the process is a solution process, the thin film. Okay, so it can improve the efficiency. So this is absolutely exceptional application in PV for perovskite. So there are some issues, and then that I would like to talk a little bit about. One is the toxicity issue, right? Net is toxic, and people worried about that. So people are trying to say, well, if net is toxic, how can we replace net, right? Can we replace net? So actually, we did that. We did that study, and then our conclusion is that it is difficult. Well, you can replace net. You can form a sort of a perovskite, and so you have a different way to replace net, right? So you can do this like homovalent replacement. Use like say we use a tin to replace net, making less toxic. Or I can use others, like say we use mixed, like use use tin, and we can also we try to, as I mentioned, the non-pairs orbital. There are other elements that are non-pairs orbitals, like say bismuth, antimony, and non-pairs orbital. How about we use that? So when we use them here, then the valence will change at the B side, and then we have something to change the N side. Then you can do splitting, you can put it there and there. What is kind of sense? So by the end, you can form this. However, what we found is that no matter what you do, right, there are different ways to do it, right? So whatever you do, you will not maintain those wonderful properties from the net, like say the spin orbital coupling, strong spin orbital coupling, because when you do that, the structure, dimensionality, the symmetry will reduce. You lose the spin orbital coupling, or you become a lower dimensional material, and then the charge transfer will suffer. So there are lots of reasons, and then why you have to use a net, right? So net is, you don't have any other option to use net. Here, this one is just to see how the spin orbital coupling will impact the bandgap and also the defect. So here is the defect. So like say, if you change orders and then the spin orbital coupling is weakened, and then your bandgap will increase as a mission, right? So then your spin orbital coupling decrease, and the bandgap will increase, and then not only the bandgap increase will give you less absorption. Another consequence is that all the defects, initially they are shallow because the bandgap increased, and then suddenly become deeper. So some of the defects that are originally good, not bad for net perovskite. When you change the dimensionality, they become bad. So after all, we examine all this, and so you can use the orders for the replacement. We found out the only option is that you can use sodium to replace net, but the sodium is even more toxic than net. Okay, so forget about this. And then you can use tin, of course, right? They're less stable. So there's no option. Okay. Finally, I want to spend a few minutes to talk about the challenges of perovskite. So everything is good for perovskite, but there's a big drawback, which is the stability. It is very, very sensitive. It's salt, right? So it is sensitive to moisture. so it can be dissolved in water. And then it is sensitive to temperature. If you heat up the high temperature, because there's also heat night, they will go away. And the world also night, if you shine at night, it becomes less stable. So you want to make a solar cell and you want to use light, right? Less stable. And then there are many others. So the stability is the biggest, the instability is the biggest issue. Okay. So when I started work on perovskite, this is a decade ago, when you make a perovskite, usually the solar cells will survive for minutes. Okay. Minutes. After a minute, and then they're gone and become yellow. So become yellow. But later, it's getting better and better. So we, through our theoretical understanding, we strongly feel that through interface engineering, you can stabilize perovskite. Okay. The reason is that all these bad things that happen, they happen at the defect site. Okay. Where you have a defect, and then all those kind of, you cause a chain reaction become bad. So if the material is perfect, and those bad things cannot happen that easily, okay? So it cannot happen easily. So therefore, interface engineering is quite important. So then we come up with this idea, we call it the rational design of noise-based molecules for stabilizing and perovskite solar cell. So what we're talking about? So we introduce some noise type of base molecules, and like say those have non-pair electrons and this that, right? So those non-pair electrons tend to coordinate with net ions. So let's say for our perovskite, right? And then you will have somewhere you will have net ions on the surface, right? So if we introduce this kind of molecules with, like say, sulfur, nitrogen, oxygen, or phosphorus, they have a non-pair electrons, right? So those non-pair electrons will coordinate with those undercoordinated net ions through the noise-based acid interaction. So we're bonded with them. And this, like say, I have molecule, like say DPPP, we call it DPP. So there's two phosphor atoms, and this that's when they tried to share the electrons with other undercoordinated ions, like say net ions, or they can also work with other transition metal ions, like say nickel ions. So when we put those in, our perovskite. So let's say this is my perovskite, right? So this is the net, right? So it has a very strong correlation with this phosphor. And then there's one side of a perovskite, and there's another side of perovskite, and it also has a net. And this molecule can bond two sides. So it makes a very good, strong bridge between this. And then we are put them together. And so make this, we are making them those surface more stable, not easy to move. And also, without this, right, it's basically essentially is a defect. So we have this one, well, possibly the defect, make the surface, green boundaries, interface more stable. And then they can also bind all those together. Right. So get this. So this will be wonderful materials, and then we, collaborators, we tried that to make solar cells. So we theoretically understand what this would work. Let's say, can we make it happening? And so that's the device result, right? So if you do not have there's a DPPP molecules to heal this green boundaries, the surface interfaces, if we make solar cells, you put it outside on the AM 1.8 1 sun situation at room temperature, you see device decrease very quickly from 20 to 23%, drop to only 16% within 600 hours. And this actually is encapsulated, right? No moisture can get in. So it is, of course, it's not acceptable because for application, this cannot happen. So after incorporating this DPP molecules, you see the device performance, the small cells, so the stability is improved so dramatically. So we say after 3,500 hours, there's almost no degradation. So that is really works. It's very big dramatic change on the stability of the device. And then we have also tried other conditions, like say we raise the temperature to 85 C, and then this in the dark, and also do this at a high temperature. So you see this one is with the modification, this one without, and here is the with 85 C. 85 C. The reason people use 85 C is that the highest the temperature as soon as it can go on the outside operation. So the hottest place, you put it there, the temperature you can get is about 85 C. That's why people try to do it at 85 C. On the illumination, you see here again. So without the DPP, it changes very quickly, and with the DPP, and it becomes very robust, right? So based on that, we think perovskite is a wonderful material, and it seems not stable, but if we can work on the surfaces, the interfaces through molecular engineering, right? Molecular engineering, we can make this stable. And not showing here, and then there are some, these are small cells. There are some module devices, I mean the real modules, real stuff. And then they can make it more stable, similar reason. However, all those devices must be encapsulated so that no moisture can ingredient in. But moisture is number one killer. If you get a moisture in this device, the perovskite would not survive. But encapsulation is not a big deal these days. So you can encapsulate larger modules. So I think with this, now we feel so confident that process solar cells can make a big impact in the real world. Right? So it is we just really need to do interface engineering. Okay, now I want to summarize my talk. So perovskite is really fascinating material because of the very unique optoelectronic properties, the defect properties, and also the low temperature synthesis, solution synthesis is really a wonderful material. Replace that will not work, and then we can make a perovskite as stable as we want. Okay, so finally, I would like to acknowledge my students, my collaborators who did the work, and then my support from Department of Energy and then NSF, and finally, I would like to thank this program, TSVP, giving me this opportunity to come here, to visit here, and to talk to you. Thank you very much.
Thank you very much. Do we have any questions?
In your calculations of band structure, how do you consider the organic cation? In the sense, we know that at room temperature, there's a high rotation.
Okay. So the organic cations in the perovskite, they are not still, the moving. So fortunately, is that those organic cations, the orbitals, the energy orbitals, they are away from the picture I show here. So they are high above the conduction band, low below the band and the valence band, because it was organic species. So in the calculation, you can, like say, take an example, like say, if you do Fa from a medium net iodine. So what you need to do is that you they have dipoles, they are different configuration. You just arrange them so that they will cancel each other, so they will not introduce too much strain in the material. So that's okay, because they don't introduce states in near the band edges. So that's one way you can do it. That's the most way that we do. We arrange them so they cancel each other, and also we can use a larger inorganic cation there to see the trend. Yeah, that's for the perovskite itself. If you have another molecules that you put on top of a perovskite, and then there's not a problem because they are not usually they are not moving like those inside perovskite. So inside the perovskite only MA, FA, and then they are rotating. But if you just do what I just said, it just be fine.
Any further questions?
So my question is, thank you
Give
very
it a
much.
moment for the mic.
Thank you very much for your presentation. My question is with regard to moisture. So after affecting, water molecules affected your thin films, right? So did you check AC parameters? Is there a change of cell parameters after contacting with water molecules?
What properties?
So I'm talking about the thin film, right? With this PB, chlorine or carbon or bromine perovskite. After affecting water molecules, did you check cell parameters?
Yeah. So you basically
Is there some change?
Yes, you mean what will happen when they contact? Yes, yes. So this has been studied. So what happens? The molecule get in, will separate the iron bond. This is not a direct reaction. They will form a new type of material. It becomes sort of kind of amorphous-like structure. So it becomes kind of transparent.
So it destroys the crystal structure and becomes amorphous. This is what you want.
Yes.
Okay.
Any further questions?
Thank you very much for the very interesting talk. I was interested in this stabilizer DPPP. Is it? I guess it was designed especially to fit with crystal.
So
How was it designed?
we are doing the design work. DPPP is not the best one yet. The reason we use DPP is just commercially available.
Okay.
Right? So we can purchase, because if we just design one, synthesizing a particular molecule is not always easy. Okay. So particularly for the theory side, we can design any molecule we want, but when we synthesize, sometimes it just won't work.
And how is it introduced? Because sometimes we use a one-step or two-step solution process to form the film. Is it introduced at the same time, or is it used after?
For this particular solar cells that we made, it's a one-step process. So we introduce them in the precursor.
Okay.
So you put them in precursor, because this molecule is fairly large, it cannot be incorporated in the lattice. They will move out, and they will segregate the green boundaries, and then two interfaces, and just what we need, right? It will do the job.
Okay, so it's completely different than passivations of solar cells. Sometimes we use a passivation layer on top of.
Right. So you can do the same. So if you put it on the top, right? So you will passivate,
Yes.
but then you will only passivate the surface. But then you won't give you the benefit to bind the green boundaries and also barrier interface. So for some molecules, it's better to put them inside the precursors.
I see.
But for some, the reason why you put it on the top is that those materials are often they cannot be put in the solution. Otherwise, you will impact the nucleation and the crystal growth.
Yes. Okay.
So if a passivator, if you are talking about a passivator on the surface, if it can be incorporated in the solution, I think that will be a preferred method. Just easy.
That's the first time I see this used with at the same time as making the film.
But there are others, other material, other molecules. People use them, just put it in the solution, and they will go the top and bottom and the green boundaries and the passivator. This is not the only one. There are others, other molecules.
Thank you very much.
Also. Another question, I'm sorry,
Mhm.
for the question, sir.
Yes, please.
With regard to electron pair, with regard to electron pair.
Mhm.
So in the composition which you showed, A, PB, something, this pair are chemically inactive, correct?
Oh, you mean the molecule?
I'm saying about the phase, right? With PB and chlorine. A, PB, chlorine. Perovskite.
Yeah, A.
So within this structure,
The perovskite structure?
within this structure you
Mm.
mentioned before, this pair is chemically inactive, correct?
Which pair? The
Lone pair.
non-pair. Yes. The non-pair. Yeah, the non-pair electron, the net.
I'm saying, I'm asking, is it stereochemically inactive? Is it correct? Because if it's active, it should be probably not cubic. It will be probably layered, maybe, you know, orthorhombic on something else.
Yeah, it is
Something.
not active. It is not active, but it has some impact, but it's not active.
It has some impact on electronic structure.
Yes.
But I mean, the next question is other modification of this phase. Do you know? Do you know any other modification
Modification to this structure?
for the structure for the phase? Yes.
Yeah. So there are other. Like say, if you introduce other non-pair electron, like say, bismuth.
I'm saying about the phase. I mean, if there are some phase transition.
Oh, it's yes. There are some other
Because it
phase.
belongs to this
Yes,
pair.
yes. This is a non-pair. Yes, there are other phase. This is the perovskite phase. There are other phase. There are people still call them perovskite, but not really perovskite. And then they don't have this octahedron structure, so they become a lower dimensional material. Like say, yeah, 0D or 1D. Yeah, that's what you said. So you will not be this crystal structure. Yes.
Okay.
Yeah, that's why this one is a non-pair. So I put this way is that when you form this structure, right? But it does not mean you will always form the structure. So it depends on the temperature. There are many things. There are other phases, and then they are not in the same structure. So in that case, and then those non-pair S electrons, they are stereotype active in that case.
Okay, thank you very much. I think then we've had enough questions for today. Let's thank the speaker again.
Thank you.